Rakitha Kaluthanthri, an experienced chemistry teacher with over 8 years of expertise. Holding a Master of Research in Chemistry from the UK, currently pursuing an MSc in Chemistry Education from the University of Colombo, and possessing a BSc in Applied Science from USJP, Rakitha dedicated to simplifying complex concepts and fostering enthusiasm for chemistry. A school teacher at a leading school in Colombo 7, a former visiting lecturer. With a proven track record, Rakitha is ready to guide you to success in your academic journey. Join the 2026 English Medium Chemistry intake today.
All right, everyone. Can you all hear me clearly? So, welcome to 2026 GCE Advanced Level Chemistry class that I conduct. So, hope everyone who's joining online also can hear me clearly, and there's no issue with the audio or the video. So, I would like to start today's class by giving a small introduction about who I am, because I believe strongly that when you're starting a class or when you're joining a chemistry class or any other class for that matter, it is important for the student to have a little bit of a confidence or a little bit of an idea about the tutor, right? So just to give you an idea, by now you should know who I am. My name is Rakitha Kaluthanthri. So I have, can you hear me now? Right. So I have been teaching since 2016, and currently I'm teaching at Ladies College, Colombo 7. There I'm working as a Edexcel chemistry teacher. However, I have been teaching local curriculum for a very long time as well, right? So I've been doing tuition for a while now. So apart from that, I would like to give you a little bit of an idea about my educational background. So I graduated from Jawaharlal University. After that, I did my master's in UK, which is a Master's of Research. So after completing that, I have been teaching at foreign affiliated universities in Sri Lanka, especially universities like ACBT and now local, but all private universities. Afterwards, I actually felt the need to, since I'm in this field, need to do another master's in chemistry education. So currently I'm doing another master's in chemistry education. Just finished the first year, so now going on the second year. So now students, that is a bit about my educational background. So, and as well as my work background. So these are some of the credentials I think as students you would benefit from knowing. I have a good idea about the curriculum, so if you have any doubts about whatever that has been discussed here, feel free to reach me out. I think all of you have my contact details. You can personally meet me here and then talk to me about any of those things after the class or during the break, right? We have a break today, that is. So anyway, with that out of the way, I would like to straight away start with our advanced level curriculum, right? Advanced level syllabus. After the syllabus, we'll talk a little bit about how you should work when it comes to A-levels, right? So I'll give you a brief idea about that. So now, our syllabus mainly consists of a few main parts. So we have a general chemistry, right? That's number one. So the first 3 lessons you come across are going to be general chemistry. I will give you a lesson breakdown as well. And then we have inorganic, we have organic, we have physical, and we have industrial and environmental chemistry. I'll just write industrial here. Right, so these are the 5 main parts you'll be learning. So industrial chemistry part is just a single lesson that is going to be found in the 14th unit, right? So all the other units, all the other parts actually contain sometimes more than one lesson. We'll see. Right. Now, I believe everyone can hear me, especially the online students. Can you confirm? So, yeah, apologies for the small technical issues we had. So now, I was talking to you about the structure of the syllabus. I was initially giving a small introduction about who I am. So you can listen to it when the video comes out, right? So we will move from here. Now, when it comes to our syllabus, we have 14 lessons. These are the lessons. I have abbreviated some names, so don't worry about it. The first lesson is atomic structure, and then second, structure and bonding and chemical calculations. Now, this part, these three are coming under general chemistry. General chemistry, right? So we have general chemistry, inorganic, organic, and then we have physical, and after that, what do we have? We have one more, industrial chemistry. So now, after general chemistry part is over, you are going to be studying a little bit of physical chemistry. Physical chemistry. So here we learn about the behavior of gases, and we learn about when chemical reactions are taking place, how energy is involved. We know apart from matter undergoing change, there is also the involvement of energy. So we are talking about that under energetics. After that, this lesson is inorganic. This is the inorganic part. Bit of a long lesson. We learn about elements coming under S, P, and D blocks of the periodic table. So we'll be learning about that in the right time. So I don't want to dive into it now itself. Apart from that, from 7 to all the way to 10, we have organic chemistry. Right? Organic chemistry. So starting from basic concepts, then hydrocarbons and halohydrocarbons, and oxygen containing organic compounds and nitrogen containing organic compounds are going to be discussed there. And then all three of these lessons again come under physical. Again come under physical. Now, chemical kinetics mainly focuses on the speed of reactions, how certain reactions are happening at a particular speed and some reactions are happening slowly. What is the reason behind it? The mechanisms of different reactions will be learned. And then we have equilibrium. Now, by now you learn only about reactions that are happening in a single direction. Reactants turning into products. So there are some reactions where both forward reaction as well as the reverse reaction can take place. Right? So you are learning about those. Right? So apart from that, we have something called electrochemistry. I think your favorite part in O levels, right? Some of you guys would have loved the electrochemistry part. Now, if you didn't like electrochemistry in O levels, don't worry, students, right? O level chemistry and A level chemistry, very different, right? I remember I hated I hated electrochemistry when it comes to the O level chemistry part, because it was mainly memorizing things when it comes to the O-level syllabus. Now, when it comes to A-levels, you learn the logic behind things, why things happen, right? So then, it is not just memorizing. It will be easier. Is that clear? So, hopefully you will learn to love electrochemistry as well. Then we have industrial and environmental chemistry. You don't just learn about industrial chemistry, you learn about environmental pollution as well. So, the reason why I broke these lessons down and I gave you an idea about which parts are general, which parts are physical, is because when discussing the structure of the paper, you have to have an idea about from which parts some questions are coming from, right? Now, when it comes to the A-level paper structure, we have to slightly talk about the A-level paper structure in the beginning of the lessons, because you have to know for what you guys are getting, you are getting ready for something, right? What are you getting ready for? You're getting ready for the final paper, That is the destination. You are starting the journey now. Your final destination is a paper, right? And sometimes I ask students, maybe after the first year is over, who has a good understanding about the paper structure. Some still don't, right? That means what? Now, you have to have your own understanding of the paper. You have to have the knowledge about the structure of the paper, because otherwise you don't know where you're going. You're just learning, right? So have a little bit of an understanding about what the paper structure is like. So I will quickly take this down, but if you want to make a note of it, I will leave it here. Do you want to make a note of this? All good? Right. So anyway, I'll share the video with you so you can actually screenshot it and go through the structure. Now, when it comes to the A-level paper structure, we have mainly 3 parts. Actually, we have 2 parts for the paper, paper 1 and paper 2. So, paper 1 has 50 MCQs. Right? 1 MCQ, 1 mark. Altogether, total marks will be 50 marks. Simple. Afterwards, we have the structured essay part. We call it part A. It has 4 main parts: part 1, part 2, part 3, and part 4. We have general, inorganic, we have physical, then organic. And organic. Each question gains you 100 marks. Each question gains you 100 marks. There are a total of 4 questions. So you will have a total of 400 marks coming from structured essay part. Each question is 15 minutes. Now remember this. Each question is given 15 minutes. Now, apart from that, you get the essay part. When it comes to essay, you have part B and part C. Part B and part C. Now, part B has questions 5, 6, and 7. Part C has question 8, 9, and 10. These 2 questions are physical chemistry questions. It comes from physical chemistry. Seventh question, now it comes from one part from inorganic. It has 2 parts, A and B. The other part comes from electrochemistry. Usually electrochemistry. These are physical chemistry. Then we have organic, inorganic, and finally industrial. Now, each of these questions, now question number 5, question number 6, question number 7, question number 8, 9, and 10, each of them is worth 150 marks. You have to do 2 questions from each part. B part 2 questions, C part 2 questions. Let's say you do 2 questions like this, the ones that I've highlighted. Each question is worth 150 marks. Each question is worth 150 marks. I'll do the math here. So there are a total of 4 questions you do, multiplied by 150 is going to be what? Altogether 600 marks. Is that clear? So for part 2 of the paper, we have 600 marks here, 400 marks here, making up 1000 marks. Right? So now comes the beautiful part. That is, for part 2, we have a total of 1000 marks. Part 1, we have only 50 marks. Your final paper is given marks out of 100. Right? So what we do is, we divide this by 20 and we get this mark to 50. Now we add the 2 and give you marks out of 100. Is that understood? So now do you understand how important the structure of the paper is? Because if you think MCQs are not that important, like, it's easy, right? You don't have to worry about MCQs too much. And if you go ahead thinking that, we have a small problem. Why? 1 MCQ is worth 1 mark. 20 of these marks is equal to 1 mark in your paper. You understand? But it's both a good thing and a bad thing, right? For example, imagine you forget and you lose 20 marks from the second paper. Then you can maybe make up your mind, I lost 1 mark. But that's not how you should think, right? But what I'm trying to say is, it comes with both good and bad, right? So, but for sure, if you improve your MCQ knowledge of how to answer MCQ, if you focus on that part really well as well, you have a good chance of scoring really well during your A-levels. Is that clear? Because if you are training yourself to be good at this, obviously you are building up your theory knowledge. You will be good at these also. But then you have to fine-tune your answering for essay parts. Understood? Right. So with that out of the way, now I just want to give you a very brief idea about this. I didn't want to stay long here because I wanted to start the lesson and go over the lesson, as we have to cover as much as we possibly can within this given small time period. So let's dive into the first lesson, Unit 1, Atomic Structure. Right? So when we are talking about things that are around us, including yourself, the chairs you're sitting on, clothes you're wearing, phones you're touching, right? All of these things, have you ever wondered, what is this thing made out of? I have a marker I'm touching here. I have a microphone I'm talking into. What are these things made out of? Right? You say, okay, this is made out of plastic. Okay, then you ask yourself, plastic is made out of what? Right? So when you ask, okay, what is that made out of? If you keep on asking that question, at one point you'll get to the point, okay, finally you'll say, okay, everything is made up of different elements. Then you can ask, okay, what are elements made out of? Now then you will, if you know a little bit of chemistry, you would know, okay, each element contains atoms. That is the smallest unit that you find making up matter, right? So back in the day also, now before we start today's lesson, I have to give you a little bit of an overview of what you can expect. So today's lesson is mainly going to be about the history of discovery of different subatomic particles. Now before we talk about subatomic particles, we have to ask the question about what ancient philosophers and scientists believed to be true about matter, right? So we are starting there, and then after that we'll talk about discovery of electrons, protons and neutrons, right? So now first of all, let's say, what is matter? Anyone has an idea? You can talk to me, like, it's not that fast. You can talk to me. I can't come any closer to you than this. What does matter? Anything that takes up space and has a mass. Anything that has a volume or anything that takes up space and has a mass is referred to as matter. Now, back in the day, when people were asking this question, what is matter made out of? One of the first understandings they had was that matter that we saw, everything that we saw around us was made up of earth, fire, air and water. Right? If you guys are watching TV series these days, now some TV series might come to mind, right? Back in the day also, a philosopher named Empedocles had this idea. Matter is made up of these four things. So we know that is not the case, but back in the day, that was the first initial understanding. But after a while, around 404 BC, there was another philosopher named Democritus who came up with the idea that if you take some element or some substance, if you keep dividing it in half, right? Imagine you take a little bit of metal, you divide it in half, and then you take that half, divide it again in half. You continuously, if you keep dividing each half into smaller halves, he said, you will eventually come to a point where you will see, or where you'll obtain a tiny particle that can no longer be divided through physical or chemical means. Right? So he said that indivisible particle is known as atomos. Atomos stood for indivisible. You can't divide it, break it further. Is that understood? Right, so initially he gave that understanding that matter is consisting of these tiny, indivisible particles. So both ins are there, so keep in mind, invisible means you can't properly see it. Indivisible means you can't break it in half again, right? So this name, atomos, was the name that he gave to this particle that he found out. Not found out, he thought is making up matter. Now afterwards, I think that after Democritus, the philosophers that were there was Plato and Aristotle. Now these guys said, no, that can't be the case. You can't have something that is invisible and indivisible making up matter. So over the past few centuries, we've been having different ideas about matter. I think the first proper theory related to matter was given out by a school teacher and a scientist named John Dalton. He gave out the atomic theory, right? So that is the first theory that initially spoke about what matter is made out of, right? So have all of you gotten the tute that I gave you? Right, let me get my tute as well. Anyone without tute? Right. Yeah, I have sent them. Oh. Comment डाल दिया. Now turn to page number 4. Turn to page number 4. So under page number 4, you can see, under page number 4, you can see the details about Dalton's atomic theory of matter. So now, Dalton mainly gave out 4 postulates. So he said elements are composed of very small indivisible particles that he referred to as atoms. Right? Democritus used atomos. He modified the name a little bit, atoms. Right? So he communicated the fact that these atoms are identical to one another. Each atom that you find in a single element are identical to one another. That's what he said, right? That was the second statement. The third statement was, I will give you the three statements here as well, and I will tell you why they are no longer applicable. These postulates that John Dalton gave out are no longer valid, but we have to learn them because, especially when it comes to your, now, when you're coming to a class, you would know after a while when you have your term test and all that, they have to ask something from the theory first, right? So one of the problems they would ask is the atomic theory of matter, right? So you have to know the four main postulates. One is all elements are composed of indivisible particles called atoms, and apart from that, all elements of the same, so all atoms of the same element are identical. You can't convert one type of element to another type, right? And all the different compounds you usually see are made up of atoms getting together in a simple numerical ratio. These are the four main postulates. So the first postulate, now you can actually write down, you can take your books out and write down these additional details you would want to have with you. You can refer to the atomic theory of matter in the tutor, but I want you to write down why they are no longer true, right? So let's take down a new heading, Unit 1, Atomic Structure, and Dalton's Atomic Theory of Matter. Dalton's Atomic Theory of Matter. Now, first one, he says, elements are made up of indivisible particles known as atoms. Elements consist of indivisible particles known as atoms. Now, this is now proven wrong. Proven wrong because we now know, now at that point he didn't know, we now know that atoms can further be divided to its subatomic particles. Can you take this down? Such as protons, neutrons, and electrons. There are other parts as well, right? You don't learn about all of that. You just learn that atoms mainly consist of neutrons, protons that are in the nucleus, and around the nucleus you have electrons. So the fact that atoms can't be divided into anything else is now incorrect. Is that clear? Atoms of the same element are identical in size and mass. in size and mass. Again, this is also proven wrong. Now, when you are asked to write in your term test or anything, like, write the Dalton's atomic theory of matter, are you going to write each point and then write proven wrong? No. Just write the 4 main points. Now, the reason why I'm giving you why they are no longer right is just to give you an idea. Now, this was the initial thought or theory that was given out by someone. Obviously, it was faulty at that point. But given the fact that that was the first theory that came out, it was revolutionary. Nobody was actually able to give a proper outline about what matter is made up of. Is that clear? Right. So then after that, so now why is it proven wrong? Actually, just to give you a brief idea without overcomplicating it, there are some elements. Now, if you take a look at different elements, by now you should have an idea that for a given element, its identity depends on the number of protons. If you have 1 proton, it is hydrogen. If you have 2 protons, helium, 3, lithium, beryllium, boron, carbon, so on and so forth. You know the first 20 elements, no? Without any issue, right? So tell me, which element has 17 protons? Chlorine, correct. So now imagine you take chlorine. Now chlorine obviously should have 17 protons. That is a must, right? So anything that contains exactly 17 protons is a chlorine atom. Okay? So now, when it comes to writing an atom and its symbol, what you write over here is referred to as the atomic number. This is called the atomic number. Basically the number of protons. And on top, we write another number. Anyone care to tell me what this number is? Mass number. Mass number. So this is the number of protons plus neutrons, or neutrons plus protons. All right. So now, chlorine usually mainly has this particular chlorine atom, but apart from this, there is another chlorine atom. Chlorine with a bit of a heavy or larger mass number. Larger mass number. For example, if you take a look at the number of protons and neutrons here, here we have 17 protons and how many neutrons altogether? 18 neutrons. And here we have 17 protons and 20 neutrons. Now, how did I figure out the number of neutrons? I know the mass number. I know the atomic number. Atomic number is basically the number of protons. Mass number is addition of proton and neutrons. So if you know addition of proton and neutrons, you can subtract the proton number and get to this. Right? So the mass of an atom depends on the number of protons and the neutrons. So do you see? Same element, but different masses for the given atom. Do you understand? So what he said about all of the atoms of a given element is the same in mass as well as size is wrong. We know very clearly there are some things called isotopes. These are called isotopes. So having isotopes disproves this point. Is that clear? All right. Take it down. Now, just to emphasize on the second point a little bit further, what he mentioned was if you take any element, in that particular element, all the atoms are the same size, same mass. Right? Now let's take something like calcium. Now calcium atoms are a bit larger. He said, okay, their size is different to the other atoms' size. Right, you can see each element consists of differently sized atoms and atoms with different masses. But he said, if you take one single element, all of the atoms in that particular element have the same mass, same size, which is now slightly wrong, right? But it doesn't mean sodium atoms can ever reach the mass of a calcium atom. That is different, right? That is not what he said. You can't have sodium atoms the mass of calcium atoms. Like sodium atoms are usually 23. Calcium is around 40. So you can't have sodium atoms reaching that mass. That's what he said, right? Sometimes situations like this can be there. Understood? Right. So the third postulate is talking to us about converting elements of or atoms of one element to an atoms of another element. They're basically asking, or he's basically stating, you can't take an element or atom of a single element and convert it into an atom of a different element. Can we do that? Chemically, we can't. We can't do that chemically. But now we can do it using nuclear reactions. But usually, students, even then, we can't just take something like sodium and turn it into gold, right? If that was the case, now there are stories called alchemists. Go read it if you are reading books and all that, right? So they, back in the day, there were people who wanted to do this, like, turn something directly into gold, right? You can't do that. That is not possible. So when it comes to the third postulate he's talking about, that is, atoms cannot be converted into atoms of another element. They are neither created nor destroyed. So first of all, we'll learn what he basically says here, right? What he basically says. If you take any given, please take down the law, first of all, that is in the books. What he specially mentions is, now if you are talking about a small chemical reaction, let's say sodium hydroxide reacting with HCl. When these reactions happen, we have to have a good understanding that there is no atom that is getting destroyed here or created here. When a chemical reaction takes place, all that takes place is the rearrangement of atoms, right? It's a beautiful thing if you are thinking about it, right? So for example, right now, you are made up of what? Atoms. Have you ever thought of what some of the atoms that currently are making you up was making up, like what else was it making up before you? Right? Have you ever thought of that? Right? So if you had some plants today, like some of the carbon atoms from the plants must be in you, right? So if you go along that line, you will see some atoms from all these cosmic events, or maybe a comet falling onto Earth, right? Some of the atoms that were there might be in you now, right? So who knows? Nobody can say no. I also thought, like, sometimes some of the atoms might have been in, like, very, prehistoric animals, like dinosaurs as well. Now making you up. Now what are you doing with it? Right? So you have to maybe, think about those kind of things just to make the subject a bit more interesting for you. Apart from that, students, one of the reasons why we always tend to balance the chemical equations is this. You can't have atoms going missing on you. When a chemical reaction is happening, all of a sudden oxygen went missing. That can happen? No, that can't happen. It's just a rearrangement of atoms. So whatever the atoms that got reacted here should be present in products. Right. So apart from that, now we learn the fact that although we can't convert, let's say, hydrogen into sodium or sodium into gold, we do have nuclear reactions taking place, right? So for example, if you take something like uranium, uranium consists of a very large nucleus filled with protons and neutrons, right? Uranium 235, that means the total number of neutrons and protons, mass number is 235. Can you imagine how big the nucleus is? So if we shoot a neutron at it, right? Our technology is now developed enough to shoot a neutron at uranium atoms or uranium nucleus. This will break into barium, and we have krypton. This is one of the possibilities, right? Releasing about three other neutrons. And these three will go and hit other uranium atoms and break them off. It's a continuous breaking after that, right? So nuclear reaction. So when this takes place, students, you can see now this uranium is broken. We turn it into barium and krypton. Is that clear? So completely two different atoms. So barium is 56, krypton is 36, and this happens to be 92. Number of protons is 92. This is 235. Right? So usually, students, nuclear reaction can disprove the third point, which is basically an atom cannot be converted into another type of an atom. So that can be disproven with nuclear reactions. Is that understood? All right. So as an example, if you want to take down an example, please take this down. Third postulate, proven wrong. Through nuclear reactions. Right? Okay. And the final point, we'll quickly talk about the final point as well. Now, final point says compounds that are formed. First of all, take it down. Take it down. The last point talks to us about the fact that when it comes to talking about different compounds, these compounds are going to be made up by elements reacting and forming structures that consist of atoms in simple numerical ratios. So you will have two water molecules form when hydrogen gas reacts with oxygen gas. So do you see in here, the oxygen to hydrogen ratio is what? 1:2. With one oxygen, two hydrogens. So this is referred to as a simple numerical ratio. But we have found out, now this is beyond the scope of your syllabus, but we have found out crystals, certain crystals that do not necessarily adhere to this simple numerical ratio. Right? There are some decimal points in the ratio. So it is not simple numerical ratio. Is that understood? So since it's beyond the scope of our syllabus, we wouldn't explain that here. But there are certain crystals, solid crystals that contain atoms making up the crystal in not very simple numerical ratios. Is that understood? Right. So with that, we can actually conclude Dalton's atomic theory. In the Dalton's atomic theory, these are the four main things, and apart from that, Dalton's atomic theory actually is nicely mentioned in the Tutor, so you can just highlight them and memorize them. This information was given to you just to let you know by now they are disproven. Is that clear? And then, apart from that, he also mentioned that the atoms look like a golf ball, right? Golf ball. So he mentioned they are spherical, right? So it's actually fascinating that he was able to come across all of these assumptions or give out all of these assumptions at that time, because with so many inventions, now we have evidence that they look like this, but still back in the day he didn't have any of that, right? Now just a small understanding that I would like to give you. Now, have you ever seen a dust particle? We say now atoms are invisible, right? But have you seen a dust particle? Now, do you know how big the Earth is? Right? So, compare the dust particle to Earth. Do you see the size difference? That is the difference between the dust particle and the atom. Do you understand? Right? So, you can imagine how big the dust particle is compared to the atom and how small the atom is, right? So a simple comparison, right? Then we move on to discovery of electron. Take a new heading. Under this we are going to be drawing some diagrams as well, so please do take a small heading. Discovery of electron. Now, when you talk about electrons, you know all about electrons now. What do you know about electrons? Not all about electrons, you have a basic idea. But you know, electrons are negatively charged, tiny particles that are usually found around the nucleus of the atom, right? But back then they had no idea, right? You know more about atoms than John Dalton did back in the day, right? So now, when you talk about electrons, we know about the charge. One scientist named Johnson G. Stoney, I think G stands for George, I can't remember now, right? So Johnstone G. Stoney, he predicted without any proper empirical data, he predicted that if matter has a smallest unit that is making up all of this around us, he predicted when it comes to charge, also there should be a smallest unit making up the charge that we see around us. Not that we see, we experience around us. Is that understood? So matter, when you keep dividing, you get to the smallest unit of matter, which is the atom. Similarly, if you have charge, if you take a look at the smallest unit of charge, in nature you will find the smallest unit of charge. Yeah, should be there. One should be there. So he said the smallest unit of charge is it the smallest unit of charge? is electron. He introduced the name electron, but he didn't have any experimental data to back it up, right? So this thought was there for a while. Then afterwards, students, scientists at that time were interested in finding out whether gases can conduct electricity. Do you understand? So they knew solids can conduct electricity, certain aqueous solutions can conduct electricity, right? Electrolyte solutions can conduct electricity. They want to know if gases can conduct electricity. One of the scientists who initially, this is a nice story. It's like a story your grandparents tell you, like back in the day, like, my grandfather did this, and then his grandfather did, right? Like that. So initially, Julius, not Caesar, Julius Plum, right? He was the one who is trying to build up the knowledge about conductivity through gas, and he had a small setup that he has prepared. But building up on his work, there was a scientist named Sir William Crookes, right? So Sir William Crookes built up on Julius Plum's work and built a new device that is referred to as Crookes tube, because he was the one who actually refined this setup and observed something that is referred to as cathode rays. Right. So first of all, let's observe what he did. He took a glass tube like this and he inserted metal plates onto both ends and connected it to a high voltage power supply, like so. Right? You had negative terminal here, the positive terminal here. So this entire part is now negative. This area is positive. Understood? Right? So afterwards, after doing this, before turning it on, let's say it is not connected here still, he evacuated this tube a little bit using a vacuum pump. That means he basically pumped out some air, making the gas inside this tube be present at a lower pressure. The pressure was lowered, right? So I can just write here, this contains a gas at lower pressure. Gas at lower pressure. Right, so he used a vacuum pump to do that. And once he connected this power supply, and once he keeps on increasing the voltage, he started to observe a small glow around here. There was a tiny glow that he observed. And gradually he saw, when he was playing around with it, he saw that this glow was moving towards the anode. Now, you should know what this is. This is a cathode, the negatively charged terminal. Cathode, and this is the anode. So he observed as this glow formed, gradually it moved towards this side, and when it connected, the circuit was complete. If there was an ammeter connected here, he would observe that the air is now conducting electricity. Is that understood? So basically, he discovered that yes, through air, we can conduct electricity, but there are requirements. What are the two requirements? I told you we use really high voltage. And what is the gas pressure? Do we have normal pressure? No. What is the pressure? Really high pressure. Not really high pressure. Very low pressure. Right? So that was intentional to see whether you are listening. Right? Just joking. Right? So it is very low pressure. And here we have really high voltage. So at very low pressure and high voltage, a gas can conduct electricity. Is that clear? And this was a bit of a glow, a bit of a bluish glow. Now, this glow started appearing opposite the cathode, but very close to the cathode. Not on the same side of the cathode, opposite the cathode, close to the cathode. It seemed like these rays are starting from the cathode. So what do you call these rays then? Cathode rays. Do you understand? So they named them cathode rays. So this equipment was the one that was used to observe this phenomena. So in honor of the discovery of this equipment, we have named this Crookes tube. To date, we call this Crookes tube. This is also referred to as the cathode ray tube, but we also still refer to it as the Crookes tube. Is that clear? Right. Shall we quickly take this down? Because I think page number 8. Page number 8. I've left some space for you to take down the Crookes tube. Please do so. You can write high voltage power supply. High voltage power supply. Gas at lower pressure. And we can say cathode rays, but cathode rays will draw them properly in a later diagram, students. When you are taking down a small note in your book, I'll give you a better diagram for the produced cathode rays. For the time being, take this down. All right. So now we'll direct our attention to this diagram over here. Now, what is taking place? Now I will erase that because I will have to use this side of the board as well. Now, when it comes to cathode rays, let's first learn what cathode rays are. I think it will be easier for us to understand what is going on here if you knew what cathode rays are. So now, I told you the cathode ray tube contained a gas, but the gas has to be at low pressure. You have to provide really high voltage. Those are the two main conditions. So they sometimes ask you, what are the two main conditions required for conductivity of electricity through a gas? Low pressure of the gas and really high voltage. Now, over here, we are trying to develop an idea about how cathode rays are formed and what cathode rays are essentially. Now, when it comes to cathode rays, students, cathode rays are formed when a particular atom or a molecule that is within the cathode ray tube. I will write down a small equation here. For example, imagine you have hydrogen gas inside the cathode ray tube. When this hydrogen gas go and sometimes knock on the cathode plate, or due to the conditions within the container, they can turn into atoms. Like so. Right? And when these atoms, as you can see over here, when these atoms move towards, let's say they are slowly moving towards the cathode. They don't have a particular reason why they go towards that side. They are randomly moving within the container. So then what happens? At one point it can go and collide with the cathode. So when they go and collide with the cathode, something happens. That is, the electrons of the atom gets removed, like shot out of the atom. Now you have to ask yourself why that happens. Now cathode is extremely negatively charged. Why is it extremely negatively charged? We have provided a huge voltage, right, to the two metal plates. So this negatively charged plate has a really high negative charge. And then what happens? This atom comes and touches the plate. Imagine this is the cathode plate, touches the plate. Now, outside of any atom is what? Outside of any atom is what? Electrons. Electrons are what? What is the charge? Negative. And this is negatively charged. And electrons, like atoms come and touch it. That means electrons and negative charge come very close to one another. As soon as they touch, the electron gets removed from the atom. Actually shot out of the atom. So that is what is indicated here. As soon as the hydrogen atom comes and touches the electrode, electron from the atom is removed from the atom and shot out of the atom. So the electron usually moves or removed and is now traveling in a path that is perpendicular to the cathode plate. That is something you have to keep in mind, right? Usually when the electron is removed, it is removed like this, and the electron is going to start traveling in a straight line perpendicular to the cathode plate. Is that understood? Right. So that is what is indicated here. So you have to understand, essentially, cathode rays are what? A stream of electrons, a beam of electrons that is traveling from the cathode side in a straight line towards the anode. Because the anode we have placed on this side, right? So they are traveling towards the anode in a straight line. Right? So this is what is referred to as our cathode rays. Is that understood? So now, you can write down a small heading. Cathode rays. Cathode rays. Can you please quickly take this diagram down? I think for the online students, you can't see the last word. It is a cathode surface, right? Here, the word, if you can't see, it's surface. Did you take it down? Did you take that down and then after this part? All right. Write this part as well. All right. Okay, done? Right, so now you have an idea about how the cathode rays are produced. Now, what else can you say? Instead of hydrogen, if I have some other gas, like let's say helium, will it be different, students? Will the cathode ray consist of anything else than electrons if you have helium here? Now imagine helium atoms are there. They come nicely and then what happens? Collide with the cathode. Electron will be shot out of the atom. Will it be anything else other than electron that is shot out? No, it's going to be the same. Now imagine nitrogen atoms are here. Same, right? Chlorine atoms, same. No matter what the gas you insert in the cathode ray tube, you are getting the same, right? So that is something you have to keep in mind. Right, so now, after we have understood how cathode rays are produced, we can actually now direct our attention to the properties of cathode rays. Now, properties of cathode rays were discovered, or actually, scientists who did experiments regarding the properties of cathode rays is Sir J.J. It is J.J. Thomson, right? So, J.J. Thomson is the one who actually discovered the electron as well with the use of the cathode rays. He used the cathode rays, did experiments with it, and finally discovered the electron. Electron was always there. He was the one who discovered it, right? It was not invention. Invention is different to discovery, right? So just keep it in mind. Now, is it okay if I erase these parts? Right. So J.J. Thomson, he initially wanted to observe. Now, there are so many properties that we can talk about. So when we are talking about cathode rays properties, we'll first talk about the fact that they are traveling in a straight line. So the experiment that he used to prove that cathode rays are traveling in a straight line is a very simple one. Now, when cathode rays are produced, students, they go towards the other end, and other end of the tube is a glass, right? So these cathode rays go and knock on the glass. And when that happens, there's a little bit of energy release. I imagine you take a ball and you throw it at a wall, you hear a little bit of sound, right? That is energy that is released. Similarly, when the cathode rays go and knock on the wall, certain amount of energy is released, but this energy is released as light. So we have a bit of a greenish glow observed, right? So I have my practical videos. I will send it to you, or you can just search on YouTube, DP Education practical videos, chemistry, English medium practical videos. You will see. So there is a greenish glow. Apart from that, if you want to really visualize the cathode rays, what you can do is you can have a fluorescent material at the back of the tube. Then when the cathode rays go and hit, it will light up really well. Actually, the fluorescent material we use is zinc sulfide. Zinc sulfide plates or anything that is coated with zinc sulfide will glow in green when cathode rays come into contact with it. Is that clear? So now, even without that, when it comes to the glass, we can slightly see that cathode rays are produced now hitting the back of the glass. But if you want to see the path of the cathode rays, you definitely have to use a zinc sulfide screen. Without that, you can't. Now, what he did was, he made a special type of tube, cathode ray tube or Crookes tube. But in this Crookes tube, right, in this Crookes tube, let's say the anode was somewhere around here, he placed an opaque object. He placed an opaque object, that means object through which light can't travel, in the path of the cathode rays. Right? So when he did that, he observed that there is a nice sharp-edged shadow that is formed at the back of the cathode ray tube. You understand? So this indicated that yes, cathode rays are in fact traveling in a straight line. If they were not traveling in a straight line, you will not get a nice sharp-edged shadow. You will get something else, right? Maybe some distorted. You can't get a clear shadow if the cathode rays are not necessarily traveling in a straight line. Right, so let's observe. So what happens is, you can see the cathode rays are traveling like so, but in these areas, you don't get the cathode rays traveling through. Is that clear? Right, so in these sections where the cathode rays were obstructed, you see a sharp-edged shadow. So this proved that the cathode rays are traveling in a straight line. Is that clear? So under the first space that I have given, students, please take down this image, this diagram. Right, you can say cathode ray tube, cathode ray tube, and this is the cathode of the cathode ray tube. This is the anode. Power supply, high voltage power supply, right? This is the opaque object. And shadow with sharp edges. Shadow with sharp edges. Obviously this part is cathode ray, so I don't have to mention that, do I? We'll still do it. Cathode rays, right? Just for clarity. Right. So under this, please write down. Under this, you can write down. When an opaque metal object is placed along the path of the cathode rays, a shadow with sharp edges can be observed. This indicates that the cathode rays are traveling in a straight line. Is that clear? So now when it comes to some MCQs or exams, if you ever asked how do you prove that the cathode rays are traveling in a straight line, this is how you do it, right? Apart from that, if you want some additional knowledge, what you can do is now what we can talk about is, now I told you earlier that the cathode rays are traveling perpendicular to the cathode surface, right? Now, just to prove that, we can get a bit of a curved cathode surface or cathode plate, and then see how the cathode rays are getting formed. You will see all of the cathode rays are getting focused onto the focal point of that curvature. You understand? So that indicates that the cathode rays were produced perpendicular to the cathode plate. It's a bit of an additional part, but I can draw a simple diagram here. I'm not going to be going into detail there, but I've done? Were you still taking down? Done? Everyone done? Right. I will erase it here. Now, if you draw something like this, you draw something like this. Imagine the does it look like a proper circle? I'm not sure. From actually, when I get down and see, it's a bit different, but you get the idea, right? This is a circle. Now imagine, now this is the center of the circle, right? Now imagine I erase the rest of it. Now I have a cathode plate that has this curvature. Now I provide it with the correct conditions like the low gas pressure and high voltage. And once we observe the cathode rays being produced, you will observe cathode rays, all of them get focused onto the center of the circle. Now, this is because cathode rays are always produced perpendicular to the cathode surface. Is that understood? Right? Sometimes in certain MCQs, this might be brought up, but this is some additional knowledge for you to have. Right, the next one is rotation of a light pedal wheel suggests cathode rays have momentum. Right, so what does that mean? What does that mean? I'll draw a small diagram here as well. Alright, so now this is a bit of a modified cathode ray tube. What you have over here is referred to as a pedal wheel. It is a small, very lightweight structure with some pedals in it. Now, usually when you were kids, you might have sometimes, like, if you go to a river or something, you make something like this and see how the pedals turn when water is flowing over it, right? So something like that, but which this one is very, very light, very lightweight. And it is placed on two rails. Rails are made up of glass, right? So these two rails are there on the rails. We have now placed the pedal wheel. Now, students, you can see the pedal wheel is here and the cathode is here, anode is here. Now, when you turn on this device, what happens is, since the cathode rays are being produced, now cathode rays start to travel towards this side. And when they try to move towards the anode, what happens? They can come into contact with the pedals of the pedal wheel. Then what happens? Just like water can rotate the pedal wheel when you are holding a pedal wheel in water, similarly, cathode rays, when they come into contact with this pedal wheel, once they hit the pedals, the pedal wheel will start to move and move forward. Start to spin and move forward. Is that clear? So now, initially when we turned on the, when we were not providing a power supply to the cathode ray tube, there was no movement in the pedal wheel. However, after we have turned on the power supply, we can see the pedal wheel moving from this end towards the anode, away from the cathode towards the anode. Why is this? Because cathode rays, now I told you, are made up of electrons. And these electrons, they can act as particles as well. So when these particles go and knock on the pedal wheel, what happens? Some of their kinetic energy they give to the pedal wheel. And the pedal wheel will start to move and spin forward. Is that clear? So this proves that these rays that are produced are not just rays like light rays. Imagine you take a pedal wheel, you put a torch to it. Will the pedal wheel start to move? No, right? Here we have electrons, basically particles that are moving at a bit of a high speed, and when they knock on these pedals will gain kinetic energy and will move. So now the pedals have kinetic energy. Kinetic energy is basically what? 1 over 2 mv to the power 2. Now for the pedal wheel to have kinetic energy, those moving particles also would have had kinetic energy, right? So if I just draw a small diagram here, you can see now these electrons, we know they are electrons, but at that point J.J. Thomson didn't know they were electrons, so I will just call them particles. So these particles were moving at different speeds, let's say. Now they have mass and velocity. If they don't have a mass and velocity, they can't have kinetic energy. So this thing proved that the pedal wheel started moving because the particles also had kinetic energy. When they came and knocked on the pedal wheel, that kinetic energy was given to the pedal wheel. The pedal wheel started to move. Is that clear? So this effectively proves that the particles had a mass and a velocity. Mass and a velocity. So we can say basically it had momentum. Is it understood? We can say, okay, it had momentum, so therefore particles also had kinetic energy, and that kinetic energy is transferred to this pedal wheel, and that's why the pedal wheel started to move towards the right hand side. Is that clear now? Do you understand? Right? So that is what this experiment was all about. So take a small diagram. This is given over here. Sorry, a space is given there for you to take this diagram. Take it down. Right. So, yeah, you have taken it down before. Right. All right. Okay. So now, after that, you can write a small sentence. When a pedal wheel is placed, along the path of the cathode rays, the pedal wheel will start to move away from the anode, so away from the cathode towards the anode, away from the cathode towards the anode. This indicates cathode rays consist of particles with mass and speed. within brackets you can write particles with kinetic energy and momentum. Right? Now, up until now, whatever that we have done, are we clear about what we have discussed so far? All good? Right? So, we have learned a few things. First thing is the fact that cathode rays are traveling in a straight line perpendicular to the cathode surface. Second one is the fact that cathode ray is basically a beam of electrons, but we can't talk about it now itself because J.J. Thomson hasn't found it at that point. So, we have to say cathode rays consist of particles with mass and momentum. Clear? All right. So then we move on to the next part. That is how they behave in a magnetic field and an electric field. Magnetic field and an electric field. Now, students, when it comes to charged particles, you will see charged particles getting deflected in a magnetic field. That is normally seen in charged particles, right? You learned about the whole Fleming's left-hand rule, stuff like that during all of us, right? So you know about these things a little bit. So when it comes to a charged particle, or if it is a charged particle, if you subject a traveling charged particle to a magnetic field, it should get deflected. So J.J. Thomson just wanted to prove the fact that these are charged. So one of the tests that he did was he subjected these cathode rays to a magnetic field. Right. So let's see. Right. So let's see what he did. So, right, thank you. Right, so now, if you take two magnets, let's say this is the north pole of a magnet, okay? And this is the south pole of a magnet, let's say. This is south pole of a magnet. Right? So, if it is not charged, if the particle is not charged, the particle should travel in a straight line without getting any deflection. And if we place, let's say, a zinc sulfide screen here, right? Let's say we have a zinc sulfide screen here. It should go straight and hit here. But when he did this experiment, he observed that the electrons, not electrons, cathode rays, they travel like this and then they get deflected like so and get hit around here. Right? So now I'm trying my best to draw a 3D diagram of it. What I'm trying to say here is cathode rays are not getting attracted towards the north pole or towards the south pole. If you think this is getting attracted towards the south pole, no. That's why I drew the zinc sulfide screen in a bit of an angle like this, just to show it is a screen that is placed straight without actually, although I draw a 3D diagram like this, it is a normal zinc sulfide screen that is placed there, right? It is not placed at an angle. So just to clarify what I mean here, I can draw a top wave. So let's say if you look at that setup from the top, would you see the south pole? No, but you will see the north pole, right? Because south pole is below the north pole in that setup, right? So imagine the cathode ray is traveling straight like this. Now, if it was going straight without getting any deflection, where do we expect it to come out? Here, right? We expect it to go straight. No problem. But that doesn't happen. When you look at it from the top, you can very clearly see it comes like this and gets deflected. So it gets deflected and then straight travel like this. Do you understand? So it gets deflected, we say, perpendicular to the magnetic field. Perpendicular to the magnetic field. Just to give you an idea, now if you are someone who's, now imagine there are two magnets here, and the observer is right in front of it, let's say, like this. I'm looking at it like this. I can't see it getting deflected at all. I see it like, traveling straight. But if I look at it from the top, I can see it goes in an angle. You understand? That means this ray comes like this, and after getting subjected to the magnetic field, it comes towards you. Not going down or not going up, it comes towards. Is that understood? So magnetic field is downwards like this, but the deflection is happening in this angle. So what do you call this angle to the magnetic field? Perpendicular. We say deflection takes place perpendicular to the magnetic field. Is that understood? Right? So that is something very strongly you should understand, otherwise it will be a problem. So cathode rays are not attracted to the North Pole or to the South Pole. It gets deflected perpendicular to the magnetic field. Right? So can you take this diagram down? And then as top wave, you can take it down there. So this is the side wave. This is the zinc sulfide plate. This is the top wave. Top wave. Any questions that you would like to ask? Now I will ask you a question. So basically, this is the cathode ray. We know cathode rays are negatively charged because they are basically electrons, stream of electrons. So if the cathode rays are getting deflected in this manner, what do you think a positively charged ray, how do you think a positively charged ray will get deflected? Will they also go like this and get deflected towards this direction or the opposite direction? The opposite direction. It will come like this and we get deflected in the opposite direction. Leave a little space for a sentence, just a single sentence. Done? All right, shall we? Okay, please write. Cathode rays get deflected perpendicular to the magnetic field. Cathode rays get deflected perpendicular to the magnetic field. This confirms that cathode rays are charged. Clear? Right, so now we have to figure out what charge it is, right? Like, come on, we know it's charged. Now what charge? What do you do? What would you do? You bring a positively and negatively charged plate close to the cathode rays, right? You figure out okay, which charge it is. Simple. So the next step is similar diagram, but you have a negative charge plate here, positive charge plate here. Then what would you observe? Usually, now when it comes to magnetic field, the deviation of the path is perpendicular to the magnetic field, right? But when it comes to electric field means when it comes to bringing two oppositely charged plates towards the cathode ray, you will simply observe cathode rays being attracted to the positively charged plate. No perpendicular situation there, right? So we have, let's say, positively charged plate here and a negatively charged plate here, and the cathode rays are allowed to move like this through them, electric field. Then what happens? This gets attracted towards the positively charged plate. Why? The cathode rays are negatively charged. Simple. Draw this simple diagram. All right. So now, by now, so one more sentence there, last sentence for that particular section. That is, cathode rays get deflected away from the negatively charged plate towards the positively charged plate. Is that clear? You can write, this confirms that the cathode rays are negatively charged. This confirms the cathode rays are negatively charged. Right. Okay. Now, students, afterwards, J.J. Thomson didn't stop here. Now, these are the properties he observed. Apart from that, he also played around with the cathode plate. He changed the metal of the cathode plate. He still got the same observation, right? He still got the same type of rays produced. The behavior of the rays were also the same, no change. Then he changed the gas inside the cathode ray tube. Right? Let's say he changed it to helium, he changed it to neon, or he changed it to nitrogen, chlorine. All of these gases at low pressure and high voltages produce cathode rays. And these cathode rays behaved exactly the same way that the initial tested cathode rays behaved. Meaning what? All the cathode rays produced in these tubes, regardless of what the gas is, regardless of what the cathode plate is made out of, is the same. This indicates that the cathode rays that are produced are identical. They are independent of the gas that was in the tube. But can you tell me, can we have no gas and produce the cathode rays? Why not? Because we need to have an atom going and colliding with the cathode plate. That's MCQ, right? They'll ask. Anyway, so yes, after doing all of that, after analyzing the behavior, he also managed to find the charge to mass ratio of cathode rays. He couldn't find the exact charge of electrons or exact mass of electrons, but observing the behavior of these cathode rays under magnetic field and electric field, he was able to calculate the charge to mass ratio based on the behavior of the cathode rays, right? Now, for example, based on how something falls, how when you throw something, how that particular thing moves under gravitational forces, you can talk about where it will land, right? So there are relationship between mass, acceleration, and the force that you have applied on it. Similarly, now you will learn about those in physics, right? Similarly, you actually can calculate, without knowing the actual mass or the actual charge of the cathode ray particles, he can basically calculate the mass to charge ratio. And he did, right? So when he calculated the mass to charge ratio, it was, not mass to charge ratio, I'm sorry, charge to mass ratio. Charge to mass ratio. It happened to be 1.759 into 10 to the power 8 coulombs per gram. Coulombs per gram. Mass to charge ratio is this many coulombs per gram. Is that clear? So now, this was a big deal. Why is it a big deal? Up until this point, we thought atoms are like a golf ball. Now we are saying, through atoms, we produce some particle that has a mass and a charge. Otherwise, you can't have a mass to charge ratio, right? So this tiny thing was in the atom, right? So we have to now change our idea about atoms. Atoms are no longer just a simple neutral golf ball. It contains some sort of a negatively charged particle. We knew it anyway contains some negatively charged particle because matter has charge. We knew when we rub plastic in our hair and then try to pick up plastic pieces, paper pieces, we knew at that point he had electricity also. He knew charge was there in matter, right? But we now know for sure there's a particle within an atom that contains a negative charge and has a very small mass. Is that clear? Through this discovery of charge to mass ratio, he communicated the fact that there is another particle within the atom that carries a negative charge, and that particle he named electron. You understand? The electron word was first brought into the picture by Stoney. Johnstone G. Stoney. He basically communicated when it comes to matter, there should be a smallest charge. He couldn't necessarily prove it, but he called that smallest charge electron. But now, J.J. Thomson has found a particle within matter that carries a negative charge. So he called that smallest tiny particle that has a negative charge electron. So by proving that there's something that has a charge and a mass, and by proving that the charge to mass ratio is this, he discovered the electron. If you say, I have something, I have seen it, right? It's there in my locker, right? You have to show it at one point. Okay, see, it's there. See, it has a volume, it has a mass. You don't have to say it has a volume and a mass. You have to basically give some evidence of its existence. This is the evidence of that existence. Is that clear? Right. So that was the most important discovery that led to the discovery that proved the presence of electrons. So the details are given here, but please write the charge to mass ratio right next to the equation that is given here in page number 10, because I have rounded off it to 1.76 here. I would like for you to have the correct mass there. All good? Now we have done the part that I aim to do actually. Discovery of the electron. Done. Okay. So, was it hard? Not stopping the class here. Was it hard? Hopefully not. Right? This part is simple. But I do believe that when it comes to some students, especially, you expect the lessons to be very, very slowed down, but I feel like if this was dragged out quite a lot, you will feel boring. So hopefully that was not the case. Anyway, so now we have identified, or we have learned about the history of the discovery of electrons. Now again, we have a bit of a dilemma. What is the dilemma? We thought atoms are neutral and like golf balls. Now we say there's some electrons in it, like negatively charged particles. J.J. Thomson is the one who said it. So he also have to give a new model, right? Like if I say, no, it's not like that, there is electrons in it. And I have to say, okay, then tell me how is it neutral? Then you have to say something about it, right? So without any experimental evidence, he said, atom is like a plum pudding, right? He's a British scientist. So he must have had plum puddings in the morning. So he was like, atoms are like plum puddings. What does a plum pudding, what do you mean by a plum pudding? Now, plum pudding, if you cut a cross-section of the plum pudding, now normally, always people draw the top view. I would like to talk about the cross-section. Cross-section, you have plums. The majority of it is pudding. You have plums in it, here and there. Right? So, closest thing we have to a plum pudding in Sri Lanka is what? What can you talk about? Something like mungara kiribat, something like that, or what do you call it? Fruit cake, right? You have cake and fruit pieces in the cake. Now, the reason it's very important to understand why it is not just like a pizza. Now, pizza is different. You have the pizza base and the pepperoni is on the top, on the surface only. The reason why he used a plum pudding is because he wanted to say they are embedded in the atom, inside the atom. And outside the atom also they can be present, but majority of it is another space. Actually, this entire space is the pudding. Pudding space was the positively charged area, he said. The plums represented the electrons. Is that clear? But together with the charge from the plums and the pudding, they form a neutral pudding. You understand? So since he used a plum pudding model, I have to explain it using the plum pudding model. So basically he said atom is like a plum pudding. Basically there is a positively charged region in which electrons are present, right? It is not just present on the surface of the atom, but throughout the atom. Is that clear? This was a bit of a faulty model. We know that now, right? We have disproven this model, but at the time, this was the initially accepted model right after the discovery of the electron. Clear? Right. So that diagram is given here, so I don't necessarily want you to draw another diagram of it. So I think the point that I'm trying to make is very clear in this diagram with a cross section in it, right? So I hope that is very, very clear to you. So the round globular, like plum-like objects represent here the negative charge, and the rest of the sphere represents the positive charge. So the total value of the positive charge should cancel off the total value of the negative charge. Otherwise, the atom is not going to be neutral. Understood? Right. So now, since we have the time, we can move on to the next part as well. Now, this part is a bit of an additional part, so I have mentioned it is additional reading to you as well in the tute. Robert Millikan's oil drop experiment. Oil drop experiment. Now, students, we still have a bit of a concern. We haven't found the charge of the electron. We haven't found the charge of the electron. So, Robert Millikan at the time was able to carry out an experiment which is now known as Millikan's oil drop test. R.A. Millikan's oil drop test. It's an interesting experiment that was conducted. So in this experiment, again students, please do understand this part that I'm going to teach you is somewhat of an additional knowledge. There won't be a structured question or an essay question for that matter about how did Millikan conduct his oil drop experiment. But there can be questions about J.J. Thomson's Crookes tube related experiments. But would you draw the diagram of a R.A. Millikan oil drop test? No. But I believe this detail will kind of put you a little bit at ease, because this is a missing piece, like a missing puzzle from our syllabus. But since the experiment was a bit complicated, we normally leave it out, right? So, and plus it is not that important just to communicate the knowledge about the charge of electron. We can just basically say electron is this charge. So we have an atomizer here that is spraying oil, right? Basically it creates oil droplets. It's like perfume. When you spray the perfume droplets come, right? Similarly, we have an oil here. As you spray the oil container, you have oil droplets coming out from it. And then they fall due to the gravitational process, they will slowly fall down. Some oil droplets are taken into a separate chamber. There's a tiny hole in the middle of the flue of the first compartment. So they will slowly fall into the second compartment. Right? Some, not all of them. And here we have a small device that is shot at these oil droplets that are forming, which shoots X-rays, which are capable of providing the oil droplets with a negative charge, right? So they are going to be negatively charged, some, right? So this flow is also going to be negatively charged. This ceiling is going to be positively charged. Now oil droplets, now they have different charges. Sometimes as they have proper charge, when they come down, due to the repulsion from the flow, they might, based on their mass and the overall charge they carry, they might levitate. You understand? So we are observing through a small microscope here what happens to each oil droplet. how slowed down their fall is, how they are levitating sometimes, right? And this, imagine it's like imagine this was the view, right? So we have a scale, we can measure the diameter of the oil droplet, right? Stuff like that. So based on that, we can calculate the mass of the oil droplet. So eventually, by the data that he has collected by observing the movement of oil droplets, he was able to calculate the charge of each individual tiny oil droplets he observed. He wouldn't have observed like 100, but imagine certain oil droplets he selected. He was able to calculate its charge. So when he found out the charge of different oil droplets, he observed something interesting. So to communicate what is interesting, I will give you a few values. You tell me what is common in all of these values. 21, 18, let's say 27, 36, 6, 12. Right? We will keep it here. Now, this is not a perfect example for what he observed, but of all of these numbers, imagine these were the charges of the oil droplets. What is the most common thing that you can see when you're observing all of these numbers? They are all divisible by 3 or multiples of 3, right? So this is 7 multiplied by 3. This is 6 multiplied by 3, 9 multiplied by 3, right? This is 13 multiplied by 3, 2 multiplied by 3, 4 multiplied by 3. Everything has 3 in it, right? So if I asked you, if all of these are multiples of 3, and these are the charges, let's say, if I ask you, what is the smallest charge according to these data? What is the smallest charge? 3. Do you understand? If you can only observe charges that are multiples of 3, what is the smallest charges that can exist? 3. Do you understand? So obviously charge is not 3. I'm taking this as an example, right? So he observed, of all of the oil droplets he saw charges that are multiples of a specific value. Then he realized, then that particular value must be the smallest negative charge that exists in nature. You understand? And he called it the charge of the electron. And that value happens to be 1.602 into 10 to the power minus 19 coulombs. Right? 10 to the power minus 19 coulombs. Is it understood? Right. So this is the charge, actually negative, minus. Right? Minus 1.602 into 10 to the power minus 19 coulombs. This was the value that he saw, or that this multiples of this particular charge was making up all of the rest of the charges you observed. Understood? Right? So based on that, he communicated, okay, smallest charge that exists in nature is this, and smallest particle that has the smallest charge is electron. By now, J.J. Thomson has found it. So he said, this is the charge of the electron. Is that understood? So simple thing, but it's like, somewhat not usually discussed in A-level classes. Just wanted you to have that information. All right. So now we have found out the charge of the electron. Millikan has found it out. So now we can move on to finding the mass of the electron. What is the mass of the electron? Don't we know charge to mass ratio? Now charge to mass ratio can be communicated like this: Z divided by M, or sometimes E divided by M. Now sometimes I don't like to use E because you think E stands for electron. No, this also can sometimes stand for charge, right? So I normally don't use this. Z divided by M is okay, right? This is another way of showing it. But E divided by M also stands for charge divided by mass. So charge divided by mass is how much? 1 point. Now charge is also negative when it comes to electrons, right? Negative 1.759 into 10 to the power, we saw 10 to the power 8 coulombs per gram. Coulombs per gram, right? And then if this is the mass to charge ratio, if this is the mass to charge ratio, if I know the charge, can I not find out the mass? Yes. We can easily find out the mass by rearranging this. So we can bring mass here and charge over here. So we have Z charge that is already known, 1.602 into 10 to the power minus 19 coulombs divided by the mass to charge ratio. Now all of these are negative values because charge of an electron is negative. Mass to charge ratio of an electron will also be negative because charge is negative, mass is not having a charge or not having a value, positive or negative value, just a mass value. So mass to charge ratio, charge to mass ratio will also be negative. 1.759 into 10 to the power 8 coulombs per gram. Right, so coulombs per gram. You can see coulombs cancel off. And when you do this, you get the mass of a electron. Right? This is going to be extremely small. 9.10 into 10 to the power minus 28 grams. 28 grams. So you can see how small of a value that is. Sometimes this value is communicated in kilograms, so sometimes MCQs might go in that direction. It is going to be minus 31 kilograms. If you want, you can take that down. So over here, minus signs cancel off. The mass comes as a positive value. Of course, you can't have a negative value for mass. Right? Now, what has happened to this per gram? You know about bringing it up, right? The exponent changes its sign to a positive sign. Now, I will quickly go over this part. When it comes to electron, you can see how small the mass is. Compared to a proton, electron is actually we can say electron is 1837 times smaller in mass compared to a proton. So you can almost neglect the mass of an electron compared to the mass of a proton. So when you're talking about the mass of an atom, we do not consider the mass of electrons. Around 99.9% of the mass comes from protons and neutrons. So the electrons, do we take their mass into account? Majority of the time we neglect the mass of the electrons, right? Because it is 1/1837 times smaller compared to the mass of a proton, or sometimes we say it is 1840 times smaller, just round it off, right? Compared to the mass of a proton. Is that understood? So we say it is negligible in mass. You will see this whenever we are talking about the atomic masses as well. All right, students. Any questions? Any questions at this point? Right. So by now we have developed a good understanding. We'll finish sharp at 6, right? Since we didn't take a break, we can finish sharp at 6, and we have covered the parts that I actually wanted to cover. But since we have the time, we can go ahead and talk about the rest of the parts as well. But I want to make a small summary, or give you a small summary of what we have done so far. We learned about the initial ideas that existed about matter, Matter is basically anything that has a volume and anything that has a mass. Now, initially Empedocles, the whole Avatar story, right? What did Empedocles say? Air, earth, fire, and water made all matter that we see around us, which was not the case. Then Democritus spoke to us about the indivisible, invisible particle referred to as atomos. And afterwards, that was thrown aside by Aristotle and Plato. And we have John Dalton's atomic theory. Now, atomic theory had four main postulates. What are those? First one, all elements are made of very small, indivisible particle known as atom. Second one, atoms of a given element are identical to one another. We learned that that is not the case, right? Third one, atoms of one element cannot be converted into atoms of another, nor can you create or destroy any atoms. Fourth, when talking about compounds, atoms are combined in simple numerical ratio. For example, H2O, CO2, right? But we do know now that is not entirely true. There are some exceptions, right? Right. So we learned about that, and then we after that moved on to the next part. The next part, bear with me a second, students. Right, sorry about that. So now, where were we? We were talking about, we were talking about electrons being discovered, right? So we finished atomic theory. Then after that, we moved on to conducting electricity through solid, liquid, and gases. Solid, liquid, we knew electricity can be conducted through it, but gases, we were not sure. So Julius Blücher was conducting experiments, and building upon his work, Sir William Crookes, he made an equipment that is now currently known as the Crookes tube or cathode ray tube. So what are the main important points when you're talking about the cathode ray tubes? If you want to observe cathode rays, what are the two main things you have to mention? You have to have a low gas pressure. Whatever the gas you take, you have to have low gas pressure, and then the other one is high voltage, right? And then we moved from William Crookes to J.J. Thomson. J.J. Thomson actually further carried out experiments to analyze the properties of cathode rays. He observed the fact that cathode rays are traveling in a straight line. Now, when I was teaching all of you, I initially told you what cathode rays were, because it's easier to know and then teach you why he did certain experiments he did. But was there another mentor to J.J. Thomson saying, okay, cathode rays are produced like this, and now go and do this test? No, right? So what happened? He himself wanted to identify whether cathode rays were traveling in a straight line. So he conducted an experiment and found out, yes, cathode rays are traveling in a straight line. That he realized they are also traveling perpendicular to the cathode surface. Apart from that, what else? What is the second test we spoke about today? Cathode rays have energy, or we can say cathode rays have momentum. Cathode rays are basically consisting of particles with mass and velocity. That was done by placing a pedal wheel along the path of the cathode rays. Third point was basically to show that cathode rays are charged. We brought a magnetic field So then after that, we confirm the charge using an electric field. After that, we also spoke about the fact that no matter what the gas we use within the cathode ray tube, we produce the same cathode ray. And we also spoke about the fact that J.J. Thomson eventually found out the charge to mass ratio of the cathode rays and thereby proving the existence of cathode rays, proving the existence of electrons. Is that clear? Right. So now we are moving on, since we have the time today, we are moving on to the next part, which is also a very important part. That is the positive rays or anode rays. Now, cathode rays are done. Let's talk about the anode rays. This is also, if you are excited about, experiments, you are going to like these parts. So, when it comes to the anode ray, students, what happened was, now, first of all, just because you are done with one experiment and everything about that experiment is done by one scientist, scientists normally don't stop there, right? For example, right after J.J. Thomson discovered the electrode, scientists could have said, everything about the cathode ray we have already found, now we'll move on to something else. Why be hung up on this, right? We can move on. No, they were like, you know what, there might be something else I also can find, right? So there was another scientist called Eugene Goldstein. So this scientist also conducted experiments with the cathode ray tube, but he made a modification to the cathode ray tube. So what he did was, if I draw a bit of a 3D diagram and the 2D diagram later on, you can see over here, he placed the cathode somewhere in the middle, like this, and he made a small modification, that is, he made sure that the cathode plate had holes in it. Cathode plate had holes in it. And then we have the anode plate here. It was not with holes in it, it was just a normal anode plate. So this was the negative cathode, this is the positive anode. And the rest of the setup was the same, sealed glass tube with gas at low pressure. And once he turned on this power supply, and when he was increasing the voltage, he observed there is another type of ray that is produced here. There is another type of ray that is produced here. Now, cathode rays are anyway produced in a cathode ray tube. Apart from that, he also observed that there were some sort of other ray that is produced. Right? Like this. They were coming from the holes. Right? So this was referred to as the anode rays. This was referred to as the anode rays. Now, these are basically, as the name suggests, positively charged rays. Now we know cathode rays are negatively charged. Anode rays have to be positively charged, right? So I will, although I say it like that, I will explain why it is positively charged. Now, if I draw a small diagram showing the cathode with holes in it like this, I will ask you one question. I told you that when atoms come and touch the cathode, what happens? Electrons will be shot out of the atom. Nobody asked me, okay, so what happened to the atom? Did the atom disappear, or did something happen to it? Yes, something happened to it. You wrote it down. What happened to the atom? Atom turns into an ion. Right? Atom turns into a positively charged ion. Simple. So basically, students, Now I'll draw another one here. So we have the hydrogen atom. I'll take hydrogen as an example. It's easier to work with. So as soon as the hydrogen atom touches the cathode, what happens? Electron will be shot out of it. And then let's say the hydrogen atom is now turned into a hydrogen ion. Right? Actually, now imagine, have you ever seen animals getting electrocuted when they touch like electric fences and all that? Right? If the charge is really high, when they touch, they get repelled. Right? Or not repelled, they'll actually get thrown off the fence. So something like that. Atoms nicely go and touch the cathode, and as the electron gets shot out of them, even the atom will be moved a little bit further away from the cathode, tiny bit. Right? Now, atom is no longer an atom, we call it a ion. Electron is removed from it, right? So we call it a positively charged ion. Now, this is positively charged. This entire area is what? Negatively charged. Now, this positively charged ion is going to be attracted by this negatively charged plate, right? So then what happens? It will be pulled towards the plate. But some areas of the plate is having a hole, like having holes in it. Then what happens? It will pass straight through those holes. Not all H plus ions will pass straight through the holes. Some will come and just land on the part that is not a hole. Then what happens? Nothing happens. It will take electron from the plate and make a atom again. Why? Because this plate is very, very negative. Now, how do you get negative charge on a plate? This plate is filled with electrons. That's why it is negative. So if a H plus ion directly comes and knocks on this, an electron will jump into this. Do you understand? Because at that point, hydrogen is positively charged, this is negatively charged. That's a very good attraction. They like to come together. Is that understood? So when they touch one another, one electron will jump into the H plus ion. So H plus ion will turn into H atom again. So usually, students, the cathode ray tube or the anode ray tube never runs out of electrons or never runs out of gaseous atoms. Why? As soon as the electron leaves the atom, it forms a positively charged ion. And that positively charged ion gets attracted again back into the cathode. When they go and touch, electron come from the cathode towards the positively charged ion. Now I'm an atom again. You understand? Then again, if the atom randomly comes and knocks on it, electron goes flying out of it. Is that clear? So they never run out of cathode rays, or in this case, the anode rays also never run out because of this phenomenon. Right. So some hydrogen ions will directly go and collide with this thing. Nothing happens there. But if they nicely align with a hole and passes through the other side, we can observe those as anode rays. Do you understand? So what are these rays made out of? If the gas was H+, what is the ray made out of? Sorry, if the gas was hydrogen, what is the ray made out of? H+. Is that clear? Since I asked you that question, what if the gas was helium? Then what are these rays? Is it H+? Obviously, you have to have hydrogen to have H+. Then what happens? You can think if the hydrogen is replaced by helium, helium atoms first of all come and into contact with the cathode. Electron will be removed. So then we have helium plus, not H+. Helium plus gets attracted, passes through the hole. We have the anode ray produced through helium plus ions. Is that understood? Now, sometimes we would like to use different gases here. Hydrogen, helium, right? Chlorine, fluorine, nitrogen, oxygen, whatever the gas you may like. Cathode ray is always the same, electrons, electrons, electrons. But anode ray, is it always the same? If you have helium here, you have helium plus ions. If you have hydrogen here, you have hydrogen plus ions. If you have oxygen here, oxygen plus ions. Nitrogen here, nitrogen plus ions. Do you understand? So based on the gas that is in the tube that we have over here, we can call it an anode ray tube. It's basically a Crookes tube that is modified, right? So based on the gas that we have used in this particular tube, the anode rays that we observe would change, right? They are not identical like in the cathode rays case. Is that understood? Right? So that is something that we really need to comprehend. So turn to page number 15. Turn to page number 15. So we have a nice diagram. I didn't leave any space for you to separately take this down. I thought the diagram was sufficient. So one other thing that I would like to talk to you about is when it comes to these positively charged ions that are formed here, they can get formed in two ways. One way I explained. When the atom comes into contact, when the atom loses an electron, you have a H plus ion produced. Apart from that, students, there is another way. That is, now imagine this short electron is now traveling really fast, right? It is traveling really fast. On its way, it collides with a hydrogen atom. Now, we are still with hydrogen, okay? Then what happens? Since this electron is moving really fast and this hydrogen also has an electron in it, if it collides in the right angle, you can see one electron from the hydrogen atom can get knocked out of the atom. You understand? So just like that, in the middle of the tube, now imagine there are electrons that are moving fast here and there are hydrogen atoms here, right? Electrons of the hydrogen atom might be knocked out, right? This is the moving electron. One electron of the hydrogen atom got knocked out. Then what do you form here? H plus ions. Is that clear? Then these H plus ions, they get attracted towards the plate because plate is negatively charged on cathode plate. And as they move towards the cathode plate, if they nicely align with the hole, they will pass through the hole. If they don't align with the hole, then they will just go and knock on the cathode plate and turn into atom again. But some nicely align with the hole, some doesn't. The ones that align with the hole will pass through to the other side and show us the anode rays. Is that clear? Since they produce these anode rays by sending, or actually we observe these anode rays starting from these holes, right? So we call them canal rays also, right? Positive rays, canal rays, anode rays, it's the same thing. Is that clear? All right, students. So I will just talk to you about the properties here and then we'll stop the class because I feel like otherwise it will be too much information for you to gather. Oh, is it? Is it not? How do you feel now? It's fine? All right. I will just quickly go through the properties and give you an idea about how we discover the proton. It's a very simple idea. And then we can stop the class. So basically today we learned about discovery of electron and we are going to learn about discovery of proton, right? Definitely not something I would have done in a normal class. So since we have a seminar set up here, I thought that's an okay idea. Let's see. Now, when it comes to this situation, we know now how the anode rays are produced. So based on the gas that we have, imagine you have gas in the tube and on the other side, let's say we talk about the anode ray. Anode ray consists of And then over here, I would like to talk about charge divided by mass ratio. Now, if I have hydrogen molecules in this tube, hydrogen molecules will turn into hydrogen atoms first, and then we'll lose electrons, and this whole story will take place, and anode rays will be produced. And the produced anode rays are going to consist of H plus ions. So if the gas contains hydrogen, ion that is produced, actually anode rays that are produced consist of H plus ions. Understood? If I use helium, we will get helium plus ions in the anode ray. I will write a few more examples. If I use nitrogen, I will get nitrogen plus ions in the anode ray. If I use chlorine, I will have chlorine plus ions in the anode ray because of this whole process. Now, when we talk about properties of cathode rays, what did we do? We learned about how they're traveling in a straight line. These guys are also traveling in a straight line. That is one. And although we call them anode rays, one of the points that I forgot to mention in the initial parts is, although we call them anode rays, did they get produced at the anode? Then where did they get produced? They got produced closer to the cathode, right? They didn't get produced over here. But since, we have and these rays moving away from the anode and away from the cathode also, we call it anode rays, initially assuming they are produced at the anode. It is not the case, right? We know actually they are produced closer to the cathode and moving away from the cathode. Is that clear? Now, apart from that, now we know different gases within the tube produces different rays, and I was going through the properties. They are traveling in a straight line. If you place an opaque object here, there will be a shadow. They have momentum. Obviously, these are ions that are moving. Massive ions. Electrons are small. These are ions. Right? So these guys are definitely capable of moving an object. Right? Apart from that, they will get deflected in a magnetic field. Why? Charged particle will get deflected in a magnetic field. And in electric field, it will get attracted towards the negatively charged plate. These are positive, negatively charged plate. It will get attracted towards it. Is that clear now? Now, apart from that, we can also study, just like J.J. Thomson did, the mass to charge ratio. Right? Sorry, I keep saying mass to charge ratio because some other lesson has mass to charge ratio. Here it is charge to mass ratio. Charge to mass ratio is observed. Now students, how do you get charge to mass? Each of them do they have different charges? What is the charge? +1. Right? And what is the mass? Now hydrogen is, atomic mass values would be 1. Helium is 4. Nitrogen is 14. Chlorine is 35.5. So which one is the heaviest here? This guy. Right? So whenever you take the mass to charge ratio, let's say MH all the way to MCl, mass to charge ratio is going to be largest over here or over here. What can you say about that? Mass to charge ratio is largest in hydrogen side or towards the chlorine side? Hydrogen side, right? Mass to charge ratio should be greater when the MH value is the smallest, right? Bear with me a second, students. I want to see if I'm visible. Yes. Right? So now you understand when it comes to this observation, as this mass increases, this is a simple mathematical relationship. As the denominator increases, overall value decreases. If the denominator is very, very small, overall value is the largest. Now, through this experiment, when he analyzed different gases, he saw one particular gas. When you use one particular gas, it has the highest charge to mass ratio. What could be the gas? You can guess. Which gas should have the highest mass charge to mass ratio? You can guess now. What is it? Hydrogen, because that's the lightest element, right? In the entire periodic table. So then, after Eugene Goldstein discovered this cathode ray tube, further experiments were carried out by Rutherford. So then he communicated the fact that this ion that is produced over here, or this particular particle that is produced here, has the largest mass to charge ratio that is observed ever, indicating this must be the particle, this must be the smallest particle carrying a positive charge. You understand? Simple theory. Like he says, in the entire world, if I analyze all of the gases, this one has the largest mass to charge ratio. That means this particular particle must be carrying, this tiny particle is the smallest particle that carries that +1 charge. Do you understand? Does it make sense? All the other particles are large. The tiniest particle that carries a positive charge. Meaning what? He said, okay, this must be the particle that carries a positive charge in an atom. Do you understand that? All the other particles had large masses, right? But when you keep on analyzing, you realize, okay, I found the smallest particle that carries +1 charge. So what is it? H plus ion. Now, when you say it like that, then you ask, H plus ion? How can it be H plus ion? We learned that proton is the positive charge particle, right? So, the same thing, right? Why? Because if you draw a hydrogen atom, now hydrogen atom consists of what? Does it have neutrons? Does hydrogen have neutrons? Hydrogen doesn't have a neutron. So if this is a hydrogen atom, you have the nucleus here. Nucleus contains of only one proton, no neutrons. And then it has an electron, right? H plus, on the other hand, doesn't have an electron also. This is H plus. Now let's say this is a hydrogen atom. This is H plus ion. What is H plus ion? Proton. You understand? That is why we call sometimes H plus ion a proton. We refer to it as a proton sometimes. That is fine. Right? So Rutherford discovered the proton by analyzing the mass to charge ratios. The one with the largest mass to charge ratio happened to be H plus ion, or when hydrogen gas was in the chamber producing anode rays. So by that theory he mentioned, okay, the smallest particle that carries positive charge in nature is produced here when hydrogen is present in the chamber. That means H plus ions happens to be the smallest positively charged particle in nature, which is then named proton. Is that clear now? So that is the discovery of proton. So I haven't left any space for you to write anything down in the tube there. So that actually concludes the discovery of the proton. Now, just to recap the discovery of the proton. Who actually initiated the experiments with anode rays? Who discovered the anode rays? A scientist named Eugene Goldstein. Who then discovered the proton? We say Rutherford did, right? And when it comes to the electron, now electron is a bit of a different story. Now electron has so many parts. Now electrons, we'll go one thing before we finish off, right? Now, electron name was given by whom? Name was initially, like, the concept of an electron or the name of the electron was initially given by whom? Stoney. And then one thing that led to the discovery of the electrode is cathode ray tube, right? Cathode ray tube. Who discovered that? Right, Crookes, Sir William Crookes. And who actually discovered the electron? Discovery is done by J.J. Thomson. And finally, students, one thing is missing here. Even when he discovered the electron, what was missing? Charge. Who discovered the charge? Millikan. Charge was done by Millikan. R.A. Millikan. Exactly. So, I know this is history, but there are MCQs about these kind of things. You wouldn't have like about 10 MCQs coming from this part of the lesson, right? Because MCQs that are seen in the paper are generally spread throughout the theory parts or throughout the syllabus. It doesn't come only from one part or mainly heavily reliant on one part. Not really, but I can't say that also they do give a preference to physical also a bit. But keep in mind, it is usually from throughout the syllabus. So this kind of question can be there. Right? All right, everyone. Before we conclude today's session, any questions you would like to ask? Any questions? All good? Right, students who are joining online, if you have any questions, let me know. Do you have any? All right, none of you seems to be having any questions. Okay. All right then, students. Just to give you a small overview, so this is a seminar setup. We normally don't have a classroom like this. We'll be doing it in a separate classroom, which is a bit smaller, more more closer to you all. I will be a bit more closer to you all than this. So just wanted to leave that out there. Right, so if you have left me your contact details, I'll be adding you to a group and we can carry out our communications in that group. All right, so that'll be all for today. Thank you all for joining. I'll see you again, hopefully, next week.